So today we are very happy to have Zhenbin Yang from Stanford University. He will talk about replica wormholes and the black hole interior. So thank you very much.
All right. Thank you for the introduction. It's a great honor to speak here. Today's talk will be based on these two papers. Um, so black hole has been a fascinating subject in theoretical physics. It is an important playground to test ideas about quantum gravity. We think understanding black hole better can maybe help us understanding better the physics of early universe. Also, black holes have a lot of connections with various fields, including strange metals, quantum chaos, quantum information, and random matrix theory. Despite that, the the biggest puzzle about black hole, that is black hole information paradox, has still been a big open question that haven't been fully resolved. The black hole information paradox talks about a tension between classical geometric description of black hole and the idea that black hole can be described by an ordinary quantum mechanics system. We call the latter the central dogma of black hole. It was essentially the idea behind holography. The central dogma contains two parts. The first is that black hole can be described as an ordinary quantum mechanics system with finite degrees freedom. The number of degree freedom is given by the Bekenstein-Hawking entropy formula, that is the horizon area divided by 4G Newton. And the second part of the central dogma is that it should evolve unitarily on the time evolution. As I said, this central dogma seems to be in tension with the geometric description of black hole. And in today's talk, of course, the central dogma haven't been proven, otherwise we won't have any information paradox. But in today's talk, we'll provide low energy gravitational path integral evidence for the central dogma. The strategy of the talk will be, we will first describe the various puzzles relating the central dogma, and then tells you how low energy gravitational path integral can solve this part of the paradox. Any questions so far? No. Okay. So let's first discuss the first puzzle. That's concerned about entangled black hole with matter field. In the geometric description of the semi-classical description, such entanglement can grow without a bound. In particular, you can have as big entanglement entropy as you can, and it can be bigger than S black hole. But if black hole is described by an ordinary quantum mechanics system with finite degree freedom, this simply cannot be true. You can simply cannot have much more entanglement entropy than the degree freedom of the system. This is a big puzzle that underlines the black hole information paradox. In the black hole information paradox, you consider forming a black hole from a shell of matter field and let it evaporate due to Hawking radiations. This describe in the semi-classical picture, this describes an evolution from pure state to a mixed state, where at the final stage, you have a Hawking radiation entangled with the interior partner. And moreover, the information of the initial state remain inside the black hole. If one draws the entropy of the Hawking radiation, then since it keeps entangling with Hawking partners, the entropy as a function of time will keep increasing. On the other hand, since the black hole is evaporating, so the area of the black hole is shrinking. So the postulated degree of freedom will decreasing with respect to time. After the crossover, then we run into the first paradox. That is, we have more entanglement entropy than the degree of freedom. So one can think what will be the correct behavior of the von Neumann entropy if we apply the central dogma. At early time, the system size of the radiation is much smaller than the size of the black hole. so the radiation can have as much entanglement entropy as it can. So we do not expect any deviations. But at a later time, the biggest entropy the radiation can get is bounded by the coarse-grained entropy. Based on that, Downpage argued that the correct behavior of the von Neumann entropy of the Hawking radiation should obey the Page curve. If we think about the Page curve and think about what essentially what's the tease of this problem, what's the tease of the first puzzle, then we find that the underlying puzzle is actually a state counting problem. That is because at a later time, the black hole, the radiations are entangled with the interior partner of the Hawking radiations, but the interior partners of the Hawking radiation have more modes than A over 4G Newton. That basically gives us this growth. You have more excitations in the interior than the actual degrees of freedom, than the biggest Hawking entropy. So that we call the state counting puzzle. Let me say it in a different context. Consider about eternal black hole. Then at a later time, the interior volume of the spatial volume inside of the interior will grow with time. And in particular, it grows without any bound. Now, if you couple this system with some quantum field theory, then the QFT degree freedom inside of the interior is extensive, so it can be much bigger than S black hole. But if the black hole is described by an ordinary quantum mechanics system with only A over 4G degrees freedom, then it cannot possibly describe so many independent modes. In other words, the interior QFT excitations must form an overcomplete basis. So how do we understand this overcomplete basis? Is the second goal of this talk. Are there any questions so far? No, okay. So the claim of this talk is that purely using gravitational path integral, we can successfully calculate the Page curve and find the correct Hilbert space dimension of the black hole. No string theory, ADS, CFT, etc. is assumed. All we need is just low-energy gravitational path integral with the inclusion of space-time wormholes. As we will mention later, the space-time wormhole also leads to non-trivial scattering process between different global charge states. So that makes a connection between wormholes and the violation of global symmetry in quantum gravity. Just a quick overview of the calculation we'll do. To talk about, to resolve the first puzzle, we will directly calculate the von Neumann entropy of the radiation. As a common trick, when you calculate the von Neumann entropy, you need to use replica trick, simply because trace row log row is not a log row is not an operator, not an expecting value of an operator. So one need to consider about n copies of the system and take the limit of n goes to 1. When you have n copy, so this trace row to the n involves gravitational path integral that contains n copies of the system. So when you do the gravitational path integral, then there are certain novel gravitational saddles enters in, which we call replica wormholes, that can connect all the systems. And such replica wormhole will dominate at the late time of the Page curve, so that when you take the limit of n goes to 1, that gives you this saturation. On the other hand, before the Page transition, this wormhole geometry is subdominating. The dominant geometry is an undisconnected geometry. So that gives you the original Hawking's calculation. And at the crossover, there's a first order phase transition. Now let's talk about the puzzle 2. I have argued for you that in order to make consistent with the central dogma, then the QFT excitation inside of the interior has to form an overcomplete basis. But what is the actual size of the Hilbert space dimension if they form an overcomplete basis? I will argue for you that the actual size of the Hilbert space is given by e to the f black hole. Our strategy will just directly construct the minimum basis of the states, I, such that any other excitations inside the black hole interior, let's call it psi, can be reconstructed. In particular, we will find that there's no particular restriction on the basis of I, so that any e to the s black hole states can be used as a basis. From that, you can just reconstruct any other state inside the black hole interior. Here I draw a cartoon. If we have a bunch of ants living inside of black hole horizon, then you can use them to reconstruct an elephant living inside the black hole. As a side remark, since those states are arbitrary, so in particular, if the QFT contain a global symmetry, then we can reconstruct states carry different global charges. In other words, quantum gravity does not allow superselection sector from global symmetry. Therefore, global symmetry is not conserved in quantum gravity.
Sorry, I have a question actually. One about the n equal to 1 limit. So that assumes analyticity, right, in n? Yeah,
so if in this analysis, you assume analyticity that a certain replica symmetric geometry dominates. But in the talk, I will tell you how to go away from that assumption. You can just do the full resummation of all the geometry exactly and taking the limit of n goes to 1. Then you find so you don't need to assume that certain geometry dominates. You just do the full. You just find this result, trace 0 to the n exactly, and then you take the limit of n goes to 1. Of course, you still need to assume that the function as a function of n is analytic. But I think that is bounded by, guaranteed by the fact that density matrix is a normalized object.
Okay. Now, in the second, for the puzzle number 2, in any quantum mechanics, I mean, even a harmonic oscillator, the Hilbert space is infinite dimensional.
Right.
Indeed, when you compute any operator, it only has a dense domain of definition. If it's unbounded, like energy, right? It's only defined on a set of measures 0, actually, on your Hilbert space. So when you mean reconstruct within a certain tolerance or error?
Yes, in certain energy window. Here the point is that the interior, the spatial volume at the interior is extensive. So you have more low energy excitations than the S black hole. So, but among those low energy excitations, those form an overcomplete basis. Like you have a harmonic oscillator at here or harmonic oscillator excitation at there. These two can be equivalent, be reconstructed. Okay. We will explain the main ideas in an extremely simple gravitation model, just to so that everyone can understand it. But all the physics can be extended to more realistic models. So, so I would hope that you can go through with me together the simplification procedure, so that everyone can understand the setup. Otherwise, if you don't understand the setup, then you won't be able to appreciate the result I'm going to tell you about. So the simplification I'll do is the following. As I have argued before, that the main puzzle about this information paradox is that the excess of the naive entanglement entropy. So that is a separate issue than the evaporation process of the black hole, where the evaporation just concerned about the energy diffusion of a thermal system to a bath. In particular, we will run into the same paradox if we replace the bath with a same temperature system as a black hole. So where we just have a thermalization process. So that's our first simplification. We will consider about a thermalization system where the bath and the black hole carry the same temperature. And here, this red and the blue arrows represents entangled Hawking pairs. The second simplification we'll do is to separate the black hole system and the bath system by cutting around this dashed line. And we abstract the radiation as simple qubits. And also, we will simplify the Hawking excitations at the black hole interior as excitations living on end-of-world brane. So that gives us this end-of-world brane model, where we just have a single-side black hole ending on end-of-world brane, where the brane allow excitations, and the bath or the Hawking radiation will entangle with a degree of freedom living on the brane. And when we describe the process of thermalization, we're just simply increasing the number of entangled pairs between the brane and the radiation. Let me rephrase the conclusion we get in this simple model. So conclusion we will get is that the von Neumann entropy of the radiation will saturate to S black hole, and states with different excitations on the end-of-world brane can form an over-complete basis. The third is that you can assign global symmetry on this brane, and then you find that replica symmetry will predict a violation of global symmetry. Let me introduce a few notation for this model. So we need to consider about this entangled state between the black hole system and the radiation. Let's call this state as psi, as a maximum entangled state between the black hole state, psi I, and the radiation state I, where psi I means the system of the black hole with the brane excited in a state I. It allows, as usual in quantum mechanics, a state can be prepared by Euclidean evolution. So this state psi I allows a Euclidean preparation where you start with a brief specification of the brane index I, and then do a Euclidean time evolution. So you cut it in the middle and do Lorentzian time evolution, you get this picture, where this asymptotic boundary got and then continued to this Lorentzian boundary, and this end-of-world brane got and then continued to this Euclid Lorentzian trajectory. Given that, we can have a boundary description of this state psi. This state psi contains psi IB, so that contains half of the asymptotic boundary with an end-of-world brane, and then it's maximum entangled with the radiation state I. Here, this dashed line means the pattern of the maximum entanglement. So we need to consider about doing gravitation path integral with respect to this state. But before that, let me do a quick tutorial on gravitation path integral. In usual quantum mechanics, when we do a path integral, we have an input and an output. The input of the path integral contains the action, which includes the fields and the metric, and then the boundary condition. And the output will be a number coming from the path integral. But when you do gravitational path integral, you are allowing fluctuation metric. Therefore, you can only specify the action and the boundary condition. For example, in 2D, you can specify the boundary condition to be a circle, half a circle, or maybe 2 circles. In this simple model I'm going to describe, I will choose the most simple gravitational action. That is just a 2-dimensional Einstein-Hilbert action, which is also a topological action due to the Gauss-Bonnet theorem. So this action will only depend on the Euler characteristic of the bulk manifold. So given the boundary condition as action, the gravitational path integral should give us a number. But that number is evaluated on all smooth geometry that's compatible with boundary conditions. For example, if the boundary is a disk, boundary is a circle, then we can fill in the circle with a disk, or maybe handle disk, etc. But the leading one will be a disk, and the topological action will just give you e to the s naught factor. If we have a semicircle, then we can fill in with a half disk by stretching an end of our brane between these two ends. Again, it's a disk topology, so the gravitational path integral will give you e to the s naught. Eventually, if we have two semicircles, then you can have two types of geometries that contribute. One contains end of wall brane connected with vertically, or the end of wall brane can connect it horizontally. The first gives you two disconnected geometries. So the topological action gives you e to the 2s naught. The second one gives you a connected geometry, and so it's a single disk that gives you e to the s naught. So that is the rule we're going to use about the gravitational path integral, that we will need to sum over all smooth geometry that's compatible with boundary conditions. As a quick notation, clarify other notation, before we are talking about the Bekenstein entropy of the black hole. Here we have a topological action with a coefficient s naught, but these are related because the Bekenstein entropy is given by the disk path integral. So as black hole in this toy model will just be s naught.
Sorry, but here for boundary, among the boundary conditions, you also have the state inside the black hole, the blue line.
The state inside black hole is specified at this endpoint. Mm-hmm. So you just specify the state at the endpoint, and then you do everything. Then you fill in because the brane can connect in this endpoint. Mm-hmm.
So just to make a connection with the story that you told us. So the degrees of freedom, how I should be thinking about degrees of freedom in this setup in which you are calculating?
Right. So the degree of freedom will be degree of freedom living on this end of wall brane. In the boundary description, that's corresponding to different boundary condition you can pose at the endpoint.
But are you introducing them?
I'm introducing them.
Okay. So what are they? Is there an action for them?
Right. In this model, I'll just not include the action. I just label them. Each of the states have the to be orthogonal on the brane, but these do not cost actual action on the in this bulk action. But in a more realistic model where you can have a JT gravity, then this brane can give you action that is proportional to the geodesic length. That is mu times L. You can do that. The action is proportional to the geodesic length of the end of wall brane.
So, and as you said, these are sort of a model, a caricature maybe of the inside modes of the Hawking radiation in partners inside the black hole.
Yes.
So you are saying, well, let's suppose that we can model them with this end of the world brane, where the end of the world brane is just labeled by a certain index I of all
Right.
the states.
Right. Mm-hmm. Well, yeah, that's right. I mean, in more realistic models, you where you have a higher dimension, you can just you impose your boundary condition, then you act operators to represent excitations, right? If you have, you can create excitations by acting operators during the Euclidean preparations. But then this acting operator can be combined with the boundary condition to give you a new boundary condition. So that essentially gives you excitations on the brane.
Hi, I'm just trying to understand which geometries you're summing over. Would there also be a twisted contribution? Or
Here we don't we assume it's there's no twisted geometry enters in. Well, but those will just give you some other corrections. Just here, here just time refraction symmetric geometries.
okay, thank you.
Okay. So are there any more questions about the setup? Now let's rephrase the puzzles in this toy model. So we have the two puzzles. There's this entropy puzzle, that is the naive entropy of the radiation is given by log K. Since this psi I are orthogonal states living on the brane. And then there's this state counting puzzle, where we have psi 1 to psi k. We can have different excitations on the brane, but this k can be much bigger than e to the s black hole. So since we form a too large a Hilbert space. Let me rephrase these puzzles in a more mathematical language. For the entropy puzzle, we can use the Hawkins method to do the calculation. We're just directly looking for the density matrix of the radiation. That is given by tracing out the black hole system. So the matrix element of the density matrix is given by this inner product, psi j. It has boundary condition to endpoints with a brane index I and j, and connected by an asymptotic boundary. So using the gravitational path integral rule, this gives us, we will fill in with smooth bulk geometries, but since there's only two endpoints, the brane can only connect these two endpoints. And since I and j are orthogonal states on the brane, this result is proportional to delta ij. So that gives you a maximum mixed density matrix, rho equal to summing over II. If you calculate the entropy of this density matrix, we get log K. When you take K to be much bigger than e to the s black hole, we get this first puzzle. As I had hint, we will directly, instead of using this method, we'll directly calculate the von Neumann entropy of the radiation. But before that, let's first look at a simpler quantity, which is the purity of the system. The purity is a trace rho squared, so it contains psi I psi j squared. So that includes two copies of the system. Two asymptotic boundaries begin from I and end in j. Now, when we do the gravitational path integral to calculate the purity, we have two smooth geometries. One geometry concern is when this end of wall brane connecting vertically, and another geometry is when it connects horizontally. When we evaluate this purity, the first geometry by summing over I and j, so the first geometry gives us single index loop. So we get k times e to the 2s naught, where this e to the 2s naught, because we have two disks. And because the density matrix need to be renormalized, its normalization is k times e to the s naught. So we need to divide it by this k times e to the s naught squared. That gives us 1 over k. For the second geometry, when we sum over R and J, we have two index loops. So we got k squared times e to the s naught, where e to the s naught is due to the fact that it only have a disk topology. So after normalization, we got e to the minus s black hole. Therefore, we see when we increasing k from 1 to be bigger than e to the s black hole, we got a phase transition such that this connected geometry dominates. This gives you a fact that the purity of the system will saturate to e to the minus s black hole. Therefore, the second running entropy saturates to s black hole, and there's no paradox. Is this clear?
So already this calculation shows that the psi's are not orthogonal.
Right. That is a factorization puzzle I'm going to talk. So why do we get two different results using Hawking's calculation and the purity calculation? In Hawking's calculation, we calculate the density matrix, the matrix element of the density matrix. That talks about psi I, psi j, and if they are different, then it's equal to 0. But in the purity calculation, when we calculate psi I, psi j squared, due to the presence of the wormhole geometry, it is non-zero. So the second equation will tell you that psi I, psi j are non-orthogonal. But in order to make consistent with the first equation, there's a factorization puzzle. It's simply not consistent with the ordinary quantum mechanics system. And there may be a lot of resolutions. The point of view I'm going to adopt right now is that if you have an actual UV complete theory, then you will find that psi I, psi j is indeed non-zero. But so the inner product will given by some delicate information. But in the low energy quantum gravity calculation, you simply do not have so many parameters. So the best you can get is that a simple gravity calculation only gives you a result after ensemble average. That is, if you imagine this Rij as some random number, then the average result of Rij will be 0, but the average result of its norm will be non-zero. So we will adopt this interpretation and to look what other features that gravitational path integral can gives you.
Why is that set of states cannot be diagonalized? Is it clear?
Well, yeah. So here we already assume we already try to diagonalize it by psi j, so that when you look at the overlap, it's 0. But still, you find that when you calculate the square, it's non-zero.
I'm not sure I understood that. If they are orthogonal, I must be that I'm not understanding the notation.
Okay.
The first line says they are orthogonal to each other.
Yes.
The second line says that the square of the inner product is non-zero.
Right.
I'm not sure I'm understanding the transition from one to another.
Well, yeah. So the first line tells you if we trying to calculate the inner product between psi I, psi j using gravitational path integral. If we are using gravitational path integral of this geometry, then it says they are orthogonal.
Yeah.
But then if we in the usual situation we'll just conclude, okay, so these two states are orthogonal, right? But here we are saying if we hold on, and if you look at the psi I, psi j squared, then using the same rule, then you find it's non-zero due to this geometry, due to this wormhole.
Oh, so but then you're introducing an additional, effective interaction, so to speak, between those states. So of course there is nothing surprising that gives you some mixing between them. I mean, imagine two free fields and they are orthogonal, and then you introduce interaction between them, and that interaction makes them mix. But you can still diagonalize. I guess that's what I'm asking. After you've taken into considerations your wormholes and written some low energy theory, which already includes those effects, can't you just diagonalize that? That's it.
Yeah, so when we do the first calculation, we also introduce the wormholes, but the wormholes just give you no contribution. So this is still zero.
I understand. Now they do give you contribution somehow. You calculated them.
When you calculate psi Sij squared, yes. Yeah. But so if it's true that the wormhole gives you some interaction between the QFT degree freedom, then you should find it's not zero in the psi Sij. You don't need to go to psi Sij squared. You should find that this is non-zero, but you don't find it. That's the key. I understand what you have in mind. You have in mind that you have a wormhole, then this at low energy give you some effective action in the QFT degree freedom. But then that interaction should appear when you just calculate a single copy of the system, when you look at psi Sij. But even taking account of the wormhole, psi Sij is still zero. So yeah, this is not an easy step to absorb, because this was still a big puzzle in, I would say, in the current research of high-energy research in understanding black hole, is how to understand this factorization puzzle. And so here I'm just taking the point of view that in the low energy gravitation passing integral, that gives you an ensemble average result. So in other words, if you have a UV complete theory, then you will find that psi Sij is indeed non-zero. It depends on this the operators in the UV. Then if you have this information, you can diagonalize psi Sij. Then you'll find that find a much smaller Hilbert space. But purely from the low energy point of view, you don't have the data of this Rij, so you don't know how to diagonalize this psi Sij. Is that clear?
So, I mean, if I understood it, you say that, let's suppose with the same rules, we compute psi I psi j and then psi I psi j square.
Yes.
In one case, we get zero. In the second, we get non-zero. So the only way to make it compatible, either the path integral has to be changed, or if we follow the same rules, one way to make these two things compatible is to say that the path integral in reality computes an average over some degrees of freedom that you don't see.
Yeah, exactly. Yeah.
Now, the one thing that I find puzzling here is that when you go from the macroscopic theory to the microscopic theory, you should also change what you call I. So is I a label of the low energy degrees of freedom, or is I the label of all the degrees of freedom?
I labels, in this theory, I labels low energy degree of freedom.
So this is an extra assumption, right? Because it's, I mean, you have to somehow to tell the theory that this I and J are just the low energy degrees of freedom.
Yeah, well, if imagine you have just, well, here, since I'm talking about this simplified model, but in a more realistic model, you can have a QFT and coupled to quantum gravity. So you just have this theory. Then this I and J will just be the QFT degree of freedom. And if you have calculated overlap, then in the you have the fixed background, you have the two orthogonal states of a QFT. Then if you look at single copy, you'll find it's zero.
So, I mean, my point is that in the three equations that you wrote, the last one, the one where the expectation, the scalar product is equal to R, really refers to other indices, to the indices of the microscopic theory, not of the macroscopic one.
Not necessary. It could be low energy the indexes of the low energy effective theory, but this R will contains information of the UV theory.
Yeah, but then this means that this psi carry extra labels, right? I mean, if you want really to distinguish them.
Yes. Mm-hmm.
Mm-hmm. So there would be psi I A, where A is some extra index that labels all the averages, all the degrees of freedom that then you average on.
Mm-hmm. Right. Now let's quick go over the von Neumann entropy calculation. So as I said before, to calculate the von Neumann entropy, we look at the J0 to the n, then we use a replica trick. So here, J0 to the n contains n boundaries. So when we fill in these geometries, we can have fully disconnected geometries or fully connected geometries. Or other type of geometries, maybe it can be connected this way. When we're thinking about, when we're increasing the 1K is much smaller than e to the s black hole, then this first geometry, then we want the topological piece dominates. So we want as many disk topology as we can. So we will have the fully disconnect geometry dominates. But if K is much bigger than e to the s black hole, then we want the maximum K index loop we can get. So that gives us the fully connected geometry. If you stare at the figure, then you find there's actually like a duality between K and e to the s black hole. For example, this void region got mapped to this solid region. So if we assume replica symmetric, then at this two limit, we can calculate the von Neumann entropy. For this one, all the gravitational path integral cancels with normalization, so we just get k over k to the n. That gives us SR equal to log k. On the fully connected geometry, then the k index loop cancels, so we just get a ratio of the gravitational path integral that gives us e to the 1 minus n s black hole. If take the limit of n goes to 1, you got s black hole. So that gives us this two asymptotic behavior. But what about the crossover, where all those geometry are same order, and we need to figure out how to do the summation. That needs us to consider about correction from other replica geometries. We will consider the limit when k and e to the s are much bigger than 1, but the ratio to be arbitrary. In this limit, we will only have planar geometry dominates. Other non-planar geometries either be suppressed by e to the minus s naught or by 1 over k. But still, we need to sum over all these planar diagrams. So how do we do that? A cool idea to think about is to view those space-time diagrams as Feynman diagrams. So we can reorganize those Feynman diagrams by thinking carefully, by thinking smartly about a new object called the Resolvent, which is a geometric sum of nth powers of the density matrix of the radiation. In terms of the boundary condition, the Resolvent will be a sum of a det ij and rho squared, etc. Now let's apply the usual rule of the gravitational path integral. Okay, is this definition of the Resolvent clear? Mm-hmm. Now we use gravitational path integral to calculate the Resolvent. So we will fill in with smooth geometries. For example, if we only have one boundary, we'll just have a single disk, and two boundaries, we can have two disks or connected disks. Then we can classify those geometries by specifying the geometry that connects the first boundary. So we will classify these two geometries as the same class because the first boundary only ends on itself. And we will classify this type of boundary as a second type of geometries where this first boundary is connected with a single other boundary. By doing that, one finds a string Dyson equation. For example, if the first geometry is only ends on have a box geometry that only ends on itself, then we will summing over a single index segment, or a row, or can have row squared. So that is the same as the resolvent, same as for the other type of geometries. So this gives you a self-consistent equation for the resolvent, and you can write down the equation that it satisfies. Here I label this gravitational path integral with n boundaries as Zn. So this is Z3, this is Z2. In our toy model, those are all given by e to the s naught. But in more complicated models, you can have non-trivial dependence on n. This geometric sum is the sum of all these classes. So after you do this summation, you got a quadratic equation for the resolvent. So you can solve this quadratic equation by the usual rule. After you get the resolvent, then you can get the density of the eigenvalues of the entanglement spectrum. That's just given by the cut around the around the real axis. In this case, you got the following density of eigenvalues. It contains a semicircle and a depth function. The depth function only appears when k is bigger than e to the s naught. So when k is smaller than e to the s naught, you just get a semicircle, and then this gives you entropy equal to log k. But when k is bigger than e to the s naught, then you get a semicircle and a depth function, and the height of the depth function grows with k. So as you increase in k, you just get a bigger and bigger depth function. So that that does not give contribution to the entanglement entropy. As a result, you find a sharp phase transition that SR is log m, where m is the minimum between k and e to the s black hole. Then there's the order 1 correction. A few comments about what I have said so far. So first, I said naive QFT orthogonal states have non-trivial overlap when we couple with gravity due to the wormholes. The second is the entropy of the Hawking radiation saturates the black hole entropy. Third, more generally, such replica wormhole geometry leads to the formula of quantum extreme islands, which can be applied to higher dimensions, like any gravitational systems. And you find the result that's consistent with the page curve. First, the fourth, the planetary summation technique can be applied to general 2D dilettante gravities, including GAT gravity. And what you find is that if the black hole is macrocanonical, then the behavior is the same. You still have a sharp phase transition, but if the black hole is canonical, then the phase transition will be smoothed out due to thermal fluctuations. So for example, that here is a result we get in our paper. If you just have a microcanonical black hole, then the transition have only order 1 fluctuation. But for canonical ensemble, you got actually a square root of n fluctuations. Okay. Yeah, I only have 10 minutes left, so let me quick talk about the state counting problem. So as we already said, this first point, that naive QFT orthogonal states have non-trivial overlap, have dramatic consequences. In particular, it means this can form an over-complete basis. So as Greg have asked, one can wonder, how do we diagonalize this basis, like find the minimum set of the states? Let's call that basis as states I, where I labels different excitations on the brane. then if we a basis of the states means any other excitations can be reconstructed from I. So the question is, can we find a coefficient Fi such that any other state A can be decomposed as a linear superposition of states I? So what is this coefficient Fi? And if and in particular, if we want to reconstruct state A, then what is the requirement on the state I and the number of states K? As a general fact, given a state A, if you want to find the maximum fidelity from reconstructing using state I, then the coefficient is given by this formula, where you should understand this right-hand side as a matrix equation, where I and J is understood as a matrix. So this is a matrix inverse multiplying by the vector J overlap between J and A. For example, if I and J are truly orthogonal states, then Fi will just be the overlap between state I and A. But more generally, if they are not orthogonal, then you need to perform this small rotation. So in other words, the maximal inner product between A and this state, Fii, is given by this formula. But still, we don't know what's the maximum value. We could only claim that we successfully reconstruct state A if this inner product is equal to 1. That is when the fidelity is equal to 1. So we will use gravitational path integral to calculate this. The key difficult part is this matrix inversion, 1 over ij. So a good way to do that is using replica trick, where we consider about the matrix to the n power, take the limit of n goes to -1. So if we take the to the n power, then we have n plus 2 boundaries, including the beginning and the last one. So we want to do this gravitational path integral and take the limit of n goes to -1. As before, you fill in with smooth geometries, since the state A is orthogonal with any other states of I. So only non-zero geometry will need a connection between the first and last boundary. The A needs to connect between themselves. But for the other type of boundaries, it can be connected or disconnected. For example, it can be fully connected geometry, or this one is a disconnected geometry. If we increasing K, such that K is much bigger, K is the number of the bases. I run from 1 to K. If K is bigger than e to the s black hole, as usual, we want maximum index loops. So the first fully connected geometry will dominate. Taking this geometry and the limit of n goes to -1, then we find this gives us the inner product between state A with itself, and if A is normalized, we got the fidelity equal to 1. That is saying we success. So here, this analysis tells us that if we have more than e to the s black hole number of semiclassical states, then any other state can be reconstructed from them. But still, there are small overlap, because what I said before is we just need e to the s black hole states. But that is the same physics as phase transition of the page curve. So that requires us to resum of all the planar diagrams. And indeed, you can do it in this model or in more general GIT gravity models, other models. Then you find that the fidelity achieves to 1 as long as K is equal to e to the s black hole for a macrocanonical black hole. And the second, there's no restriction on the choice of basis. So any e to the s black hole semiclassical states can expand a complete basis. The third, let's talk about the physics of remnant. In the previously, people have idea that maybe at the end stage of black hole evaporation, Planckian physics stop it to be fully evaporate. So you get a remnant with a small size but large interior, can give you large degrees of freedom. Those are the semi-classical degree of freedom I'm talking about. And this analysis shows that despite the large interior gene, the actual degree of freedom, quantum mechanics degree of freedom, is much smaller. And so there's no thermodynamic instability of the remnant if you accept my rule. So in this sense, maybe it's better to call the remnant as a faint remnant. It does not actually have so many degrees of freedom. The final point, if you consider about the black hole, nothing prevents the black hole to be fully evaporate. So after fully evaporate, you got a closed universe. Then this extrapolation of the result will tell you that the Hilbert space of a closed universe is one-dimensional. In other words, any state I are equivalent, but with a random phase, e to the I theta. This also fits nicely with the idea of the final state projection of the black hole. Okay, I have 2 minutes left.
You can take some more if you need a minute.
Okay. Okay, but I shouldn't rush. So are there any questions about this side?
Well, I don't understand one thing. You say that you have in e to the s states, so you want to expand every single state in your effective theory in terms to e to the s states.
Yes.
Right.
Mm-hmm.
And now you say that the fidelity happens when this number of states, the number k. Mm-hmm. So maybe I forgot which is which. These I are the states that you get in your field theory. Right? For instance, you have a black hole that is very, very big, and then you have in field theory a number of degrees of freedom that's proportional to the volume times the cutoff. To some power.
Yeah.
So this can be much larger than the number of states in the black hole.
E to the s black hole, yes.
Yeah. Okay, so I am not surprised at all that with these k states, you can reconstruct e to the s states, because e to the s is less. But don't we want also the opposite? Don't we want to say that in reality, there are only e to the s independent states?
Okay, so I think I didn't explain my point very clearly. Here I'm saying out of this, those large number of states, you can just pick up e to the s black hole of the semi-classical states. So in other words, you just pick k to be e to the s black hole.
Mm-hmm.
Then you can reconstruct any other states from those e to the s black hole semi-classical states.
But how do you see that actually the states that you would say are completely orthogonal or are orthogonal in the low energy theory, in field theory, in reality are not orthogonal? Where do you see that?
Oh, that is this wormhole calculation, right? This point, right? When you look at this.
So this is the initial one that you had that showed.
Yeah.
And we don't have any idea of how is that compatible, say, with locality, right? The black hole is very big, it's galactic size, and you have, say, states that are localized.
Right. So you say, yeah. So there's a large. So in other words, there's like a large number of null states, so that all these large volume number of states are like a kind of equivalent and reduced to e to the s black hole physical states.
Mm-hmm.
Yeah. Yeah, I don't think we have any idea of how this actually happen. For example, how if we think about our universe as a closed universe, then how that is consistent with our universe. But for a black hole, if you just view it from an outside system, that is what's happening. So in other words, we don't have a clear understanding how that is consistent with an infalling observer. In other words, what will be an infalling observer observe if those states are equivalent? Like if there's like a shock wave or firewall at the near the horizon, is the firewall state equivalent to a non-firewall state? that's still a big puzzle. Finally, let me maybe talk about a question that I often asked: are these wormholes real? So you have calculate the entropy, but those like the replica wormholes are kind of just a mathematical trick. So in some aspect, those wormholes are not real. The replica system is just a mathematical trick. But in some aspects, they are real. The first point is that I would say the physical consequence of this wormhole are real. Like the entropy of the Hawking radiation is a physical meaningful quantity, or the Hilbert space dimension of the black hole is again a physical meaningful quantity. So the consequence of the wormhole are real. And second point is that such replica wormholes can appear in the physical process when you consider about scattering probabilities. The scattering probability, once you have a scattering amplitude, the scattering probability is given by the scattering amplitude squared. In this case, if you want to calculate the scattering probability between state psi I and psi j, then you need to consider about psi I, psi j squared. As I have said, when you have, in this calculation, the wormhole can contribute. And actually those are, in some cases, are semi-classical saddles. So those are real effects. And what are the consequences of this effect? For example, this will tell you that global symmetry is violated in quantum gravity. We can simply choose state psi I and psi j to carry different global symmetry charges. So if the theory have a global symmetry, then you will prohibit to psi I, psi j to have non-trivial scattering process. But if you but on this wormhole geometry, these states I and j can form a singlet between these two copies. So if you have a QFT with global symmetry, it will not prevent you to have a process that living on this wormhole. In other words, this wormhole can lead to a non-trivial transition probability between different charge states, so that global symmetry is broken. And on the other hand, gauge symmetry is preserved. Yeah. On the other hand, gauge symmetry is preserved, since you can understand the following: if just understand as the Gauss's constraint across this wormhole will impose singular constraint across this wormhole, so that will impose singular constraint on I and j. Or you can understand more abstractly: whenever you have a bulk gauge symmetry, then it induced global symmetry from the large gauge transformations. And in the presence of two boundaries, single gauge symmetry will induce two global symmetries, each living on this asymptotic boundary. Therefore, each gives you a singular constraint between I and j. Any question? Okay, I think it's running late. So let me quickly conclude. So using in this talk.
Hello. Yes, I mean, maybe this is a very basic question, but why can we tell that global symmetries are explicitly broken? Like, what is the calculation? Because I imagine if we have an average on, for example, on the dual side, maybe the fundamental quantum properties of the quantum numbers get washed away, and those syntheses I and j maybe are not really describing the global charge. Maybe they are just like an average, and that's why the overlap is non-zero, and we don't have like selection rules. What does it mean that gravity breaks global symmetries? Maybe this is a very dumb question, but what does this mean?
Okay, so there are 2 points. So if you think about it from the idea of ADS-CFT, then the global symmetry does not corresponding to any symmetry for the boundary theory, because any global symmetry at the boundary becomes a gauge symmetry. Okay, so to talk about global symmetry, you need to talk about the bulk effective theory. So here I'm talking about the bulk effective theory, which contain both gravity and QFT with global symmetry. So you can have operators that are charged under this global symmetry. That can be with I and J. So you evaluate, say, so you can evaluate, say, OI, OJ, where OI, OJ contains different different global charge. You can then in the boundary theory, you look at OI, OJ squared. Then you find it's non-zero due to the wormhole. Then tells you that so non-trivial two-point function between two charged states and two charged operator tells you that global symmetry is broken.
Yes, I understand that, but for example, it's the same calculation as you did before. I mean, all those IJ relate all the quantum numbers. I mean, there's no like inner structure that can give selection rules or anything when you do that calculation. That's my question in reality.
Oh,
if there
okay.
are no like inner structure that maybe they're orthogonal and we don't see it because we are not really using the gauge theory, but not gauge theory, the real properties of the overlaps of two states with different quantum numbers.
Good. Okay, so in our paper we do the calculation where you have 2D gravity plus ZK BF theory. So the ZK BF theory contains ZK zero form symmetry and one form symmetry. Then you can directly calculate. So by your standard point of view, that contains ZK global symmetry. Then you can directly calculate this scattering process, and you can find it's non-zero. It's not just due to this stupid model I'm talking about. I mean, I'm using this model to illustrate the basic ideas, but all those can be extended to more realistic models. Okay, so just a few future directions. In the talk, I'm talking about the connection between replica wormholes and the first part of the central dogma, that black hole can be viewed as a quantum mechanics system with finite degree of freedom. But there's also a second part, which says it should evolve unitarily. In an ongoing project with Douglas Stanford and Sheng Yao, we are investigating the relation between unitarity and wormhole. And we think there are these handle disk geometries that contribute, that is important to understand the unitarity condition. And second, when I first started my grad school, Juan told me why we start black hole, because it has close connection between cosmology. So it's also a good idea to, with this recent development of black hole, it's also a good idea to apply this in the context of cosmology. And here there are ideas that making the connection between no boundary proposal with a wormhole. And in some models, you find that if you apply the no boundary proposal, not for the wave function, but for the density matrix of the universe, then in certain situations, there's a transition from the Hartree-Hawking wave function to a wormhole state. So that's an ongoing project I'm currently doing with Victor Gobenko and other people. Thank you.
Thank you. And so,
thank you. There's a question.
So, well, one question: when you said we for the work that you did, who were your collaborators?
When we say we, so this, so the main part of the of this work is based on collaboration with Jeff Pennington, Douglas Stanford, Steve Schenker. And that is mainly the calculation of the page curve from the replica wormholes, and also with collaboration with Luca Ilussi and Po Shen Xin on this relation between wormhole and global symmetry, and also this this constructing of the Hilbert space of the black hole interior.
Thank you.
Thank you.
Questions, especially, so I've seen that we have quite some graduate students, so anyone wants to ask any question. Again, there is no question that's too simple or trivial.
So Zhenbin, you mentioned and most of the calculations you did in this 2D model, but you referenced that the similar replica trick, et cetera, would work in higher dimensions as well. So what are the complications that come in? I assume it's not just a simple porting. Like, is it? Yeah.
Yeah. So there are several complications one will encounter. The main thing is how to construct these wormhole geometries. So it has two complications. First is in high dimensional gravity, you need to look at wormhole geometries, you need to look for semi-classical saddles for this high dimensional gravity theory. And there's another complication is that the QFT complication. Here, I'm just using the state living on end of Wall brane. So that's just the most simple QFT quantum mechanics degree freedom you can get. But more general situations, you need to consider about QFT, like more complicated QFT system living on this coupled with gravity. The physics is rather the same, but you need to consider about the back reaction from the QFT, from the stress tensor to the metric, and etc. So there are certain level of complications that one will have.
But so, for example, is the broad outline of the page curve proven in higher dimensions already, or is it still just in 2D and in JT gravity, for example?
Okay, right. So the explicit calculation is done in 2D, and as I said, but from the replica calculation, from the replica wormhole geometry, you can derive this quantum extreme island formula. Like just to assume that in the high dimensional calculation, you can also have this unconnected wormhole geometry. But the point is, when taking the limit of n goes to 1, you recover the original geometry. So that gives you a formula that you can use in the original classical saddle. So that can be applied to higher dimensions. So the jump is lies in the assumption that in high dimensions, when you consider about n copies, they have this unconnected wormholes. But the derived formula can be applied because it only depends on the classical, the original saddle. And is that?
Yeah, thank you. Thank you.
Can I think of the replica trick as a regularization of the expression for von Neumann entropy? You start with log rho. I'm sorry, yeah, log rho, and then did the trick. Is there any other kind of mathematical representation of the same expression? And if there is, then what would in that case be replacing the role of wormholes? Seemed like in this case connected to the fact that you had n copies.
Yeah.
So,
right. The other way I know is if you have rho, you diagonalize it, you find the spectrum, and you calculate it. But unfortunately, that isn't an accessible rule we can use in the gravity calculation, because that assumes you know the matrix element of the density matrix to high precisions. And on the other hand, this trace rho to the n, you can just simply calculate using, it does not need to know each matrix element of the density matrix. So in other words, if you're trying to directly diagonalizing rho, then you need more information than what we can offer you now, because you need to know all the matrix element of the density matrix, and you need to know how to diagonalize it. The matrix element of the density matrix haven't needs the information of this Rij, but that Rij cannot be provided from the low energy gravitational calculation.
Yeah, I was thinking of some kind of other mathematical representation of a log. I don't know, some kind of integral or anything along those lines. In which case you wouldn't have in that expression log itself.
You can have a zeta function, right?
Oh, here you go.
Yeah, like a zeta function type of regularization where you take the T to the S.
That's right. For instance, yeah.
That I would think will perhaps the same, like roughly be the same as what we said.
I mean, you will have to compute the trace of the exponential of T times the density matrix. So maybe at the end, when you expand the exponential.
Well, you expand, you get to this trace to the end. I think probably it's the same as the resolvent calculation.
Maybe.
The resolvent is 1 over lambda minus rho. You can do a constant integral of lambda, you get e to the minus t rho.
Yeah, yeah.
So just to clarify this for myself, so there are the two key computations for this question of the Hilbert space of the interior are one that shows that the overlap of two states square is actually non-zero. So that tells you that you are taking some sort of average when you do the functional integral. And then your second computation using the replica trick showed that the dimension of the Hilbert space, so the number of independent vectors, is e to the s.
Yes.
Am I correct with that?
Right, that's correct. Yes. There's another question.
Let's see. Can you read it in? Okay,
yeah. So the question says, on the one hand, the information paradox seems solved, but on the other hand, the black hole violates global symmetries. So if a certain total baryon number falls into a black hole, is that information preserved that as it would be in quantum mechanics, or is it lost? Quantitative estimation of amount of global symmetry breaking. Okay, so right, so here I said that if you have a certain baryon number fall into the black hole, then the total baryon number is not conserved because global symmetry is broken in quantum gravity. And the effect is given by non-perturbative gravitational effect. So it's e to the minus n effect. But that does not mean that the information is lost. Well, just because you don't have this this symmetry. So if you don't, in general, if you don't have symmetry, so you have some scattering channel from baryon to lepton, it does not mean that you lost the information of the baryon. It just means you need to be smart in reconstruct the initial information. And there's one part of the story I haven't tell you is that you can reconstruct the information in the interior from the radiation using something called path map, where you can acting on the given the density matrix of radiation, you can recover the initial information. That essentially is the same as the calculation. If the black hole evaporated, would there be correct baryon number? No, I don't think. Yeah, if the black hole fully evaporates, I don't think you have a conserved baryon number. I mean, the idea that black hole does not preserve global symmetry is not a new idea. It's like a focus law. I think it was first argued by Hawking when he finds that black hole evaporates. So if you have a heavy baryon falling and when it evaporates, you have the light particles coming out. So that gives you a process where global symmetry is not preserved. But here we show it more specifically how it appears in other quantity, just the scattering probability from the wormhole.
I'm sorry. I understood that the standard lore is that you don't, black holes have no hair and you don't have anything but charge and spin and so on and mass, and not in particular global quantum numbers. But then I remain confused about the relationship of that and information preservation, because still it seems to me that, like in quantum mechanics, you wouldn't. Am I just not maybe I'm not understanding what the information paradigm.
Imagine in quantum mechanics, you have an approximate symmetry.
Imagined.
Sorry, you got lost. Yeah, can you say again?
Oh, sorry, I have a bad internet. That's why I turned everything off for a while. Anyway, it seems to me puzzling in terms of an information and unitarity point of view. But maybe you're just saying that if in the theory, or if in the original microscopic theory, there was no breaking of this particular global symmetry, then I just don't see how you can have that come about consistently with a conventional idea of unitarity.
Yeah.
And in particular information. Am I being too naive, I guess?
Oh, no. Okay, my answer to your question is that I think the replica wormhole calculation tells you that in the microscopic theory, there must be no global symmetry. The global symmetry must be explicitly broken. So if you think about it,
I see. It's just another source of global
symmetry. Yeah,
really. Okay, I see.
That's an excellent question. Analogy would be a Spaleron. Perturbative standard model, baryon number is preserved.
Right.
Spaleron non-perturbative violate baryon number, yet of course all the processes are unitary. So it's not.
Yes. Okay. Wonderful.
Other questions?
Thank you.
Thank you. Thank you for the questions.
Hi, Zhenbin. I was curious. So all the geometries you talked about, were they all saddles at the relevant point at which they needed to contribute, or did you ever have to include geometries that weren't?
Yeah. So it depends on what you do, but the main part of them, most of them are saddles. There we have what we trust the calculation the most.
And which parts were the non-saddles relevant in some part of the?
Well, I guess in all of them are like saddles. Well, it's not obvious from this toy model they are saddles, but in other models you can check they are indeed saddles. But to keep the presentation simple, I choose them to this model. I think the only non-saddle will be this one. But I haven't discussed it in wormhole in cosmology.
Thank you.
Mm-hmm. Yeah, but in the previous discussions, most like all of them are saddles.
And if I understand, in your model, you don't need to include higher genus surfaces because they are always subdominant in
right.
all the regimes.
Right. Well, that you can understand from the boundary point of view, because those page transition or this state construction are property of the. If you think about it sounds like some chaotic system. This page curve or whatever this state reconstruction are property of the eigenstates of the system. And the higher genus saddles, the higher genus properties are property of the energy level repulsions. So those are distinguished features. So if you just want to talk about the eigenstates, then you don't need to talk about level repulsions.
Other questions? If not, we can thank our speaker for the time he devoted us. So, Zhenbin, thank you. And then we stop recording now. If people want to stay on, they can. Okay, so.
Okay, thank you. Stop sharing.
Yeah, thank you. Nice talk.
Thank you.